With modern DC locomotives, like our SD60i, the diesel engine is used to turn the main generator, which is actually an alternator producing AC current. This AC current is rectified, changed from AC to DC, at the main generator. The main generator's DC current output is then fed directly to the DC traction motors. With AC traction systems, we start out the same way. The diesel engine turns the main generator, AC current is rectified to DC. Now here comes the difference. The main generator's DC output is then fed to two computer-controlled inverters, one for each truck. The inverters convert the DC current back to AC, which is then fed to the AC traction motors. By controlling the voltage and frequency of the AC current, the inverters control the speed and power of the AC traction motors. Although AC motors have been around for a long time, until just recently, AC motors just couldn't match the starting torque of DC traction motors. Because of this, DC traction motors have been the choice since the early days of the diesel electric locomotives, right up to our SD60i locomotives. Along with this high starting torque, DC motors brought along many limitations. DC traction motors are equipped with commutators and carbon brushes, which are subjected to very high current loads. Applying high current loads to a DC motor that is not turning or turning very slowly can cause severe damage to the commutator and the brushes if the high current is applied for too long a period of time. At the upper end of the locomotive's amp range, this can be just minutes. This is referred to as the short time ratings for the locomotive's traction motors. AC motors are not equipped with commutators and brushes, so AC traction motors do not have this limitation. That means no short time ratings. And now, because of advances in computer and inverter technology, the starting torque of the SD80MAC's AC traction motors actually exceeds its older DC counterparts. The nature of these AC traction motors also makes them less susceptible to wheel slip. DC traction motors also require high current levels or amps to produce high power. Heavy traction motor leads and conductors must be used to carry that high current, and the high current also produces a great deal of heat, which further limits the DC traction motor. The SD80MAC's AC traction motors rely more on the frequency of the alternating current to produce power. For that reason, you will not find an ammeter on the control stand display. Instead, the locomotive's computer system calculates and displays tractive effort in pounds on the cab display for each AC locomotive. Tractive effort is the actual force the locomotive, less its own rolling resistance, exerts at its coupler. Now the engineer can get an actual indication of how much pulling power he is applying to the train. This is a great feature. Let's go up and take a look in the engine room. But before we do that, there are some important safety considerations with AC locomotives we need to review. Unlike the high voltage circuits found on conventional DC locomotives, the AC traction system found on the SD80MAC and all AC locomotives requires components to store energy in the form of high voltage. These high voltage circuit components are referred to as DC link capacitors and are capable of storing a charge of 3600 volts DC. This high voltage can be present in the high voltage or traction control cabinet of the locomotive even when the locomotive is shut down. The high voltage traction control cabinet on the SD80MAC is located just behind the cab with access from the running boards. Only qualified maintenance personnel are allowed to access this area of the locomotive. For the purpose of protecting personnel and equipment, this locomotive is equipped with 3 automatic discharge systems which will reduce DC link capacitor voltage to 0. The first system functions whenever the reverser handle is moved into the neutral position. Bleeder resistors will bleed off the capacitors to 0 volts. The second system will discharge the capacitors through the dynamic brake resistor grids anytime the isolation switch is placed in the isolate position. The battery switch must be closed and battery voltage must be present for this to take place. The third system will discharge the capacitors whenever the diesel engine shuts down. When the diesel engine shuts down, the auxiliary generator ceases to produce output. The inverters require auxiliary generator output to function properly. So when auxiliary generator output is lost, the inverter triggers a protective electrical crowbar. This electrical crowbar creates what is essentially a direct short circuit across the capacitors, which discharges them instantly. To be certain that the automatic discharge methods have functioned properly, a system self-test can be executed using the control stand display. If the self-test determines that voltage has not been removed, the user will be notified by computer display messages and the sounding of an alarm. Let's go take a look in the engine room. We'll start on the left side, work around the locomotive, and then right up into the cab. Just behind the cab is the high voltage traction control cabinet. This is where the capacitors, inverters, and high voltage switchgear are housed. Again, only qualified maintenance personnel are authorized to access this area of the locomotive. Moving back, in this area, the main generator, turbocharger, and turbocharger aftercoolers are located. This is referred to as the generator end of the diesel engine. The main generator is connected directly to the crankshaft of the diesel engine, which is housed in this area of the locomotive. This 20-cylinder, 2-cycle, 710 diesel engine is the heart of this powerful locomotive, pumping out 5,000 horsepower. The basic construction of this diesel engine is the same as you would find on all EMD locomotives. On the top of the diesel engine is the exhaust manifold. Below that is the top deck area, the cylinder test cocks, airbox covers, and crankcase covers, and of course the lube oil dipstick for checking the lube oil level of the diesel engine. Moving back, we are now at the accessory or free end of the diesel engine. This is where the water pumps, oil pump, and electronic fuel injection components are located. Notice there is no governor. It has been replaced by the electronic fuel injection components. Engine water fill and the water level gauge are accessible from this area. Further back is the water expansion tank, the fuel oil filters, and below the fuel pump and lube oil filters. These next doors access the AC cabinet, which houses the electrical components for the electric motor-driven equipment and traction motor blowers, the radiator fans, and the electric motor-driven air compressor. This cabinet contains high voltage. This area at the rear of the locomotive is where the dynamic brake grids are located. Moving around to the right side of the locomotive, these doors access the electrically driven 4-cylinder air compressor. Inside, there's a dipstick to check air compressor oil level that should be checked whenever the diesel engine lube oil is checked. Behind the next doors, the Lube Oil Cooler is located, as well as the air supply cutout cocks for the horn, split cooling system valve, and the air start magnet valves.